Hello everybody, welcome to the GCSE Physics live stream. Today it's the 17th of April, it's my third live stream. I'm going to be doing something tonight, I'm going to be doing something again tomorrow, having a little bit of a break over the weekend, then I'll be back into it on Sunday night. Obviously I've got my branded mug here. You can't buy these anymore, but some of you might recognise this if your teachers have one. I gave away about, I think, 500 of these last year. So do let me know in the chat if you've seen one of these in school, in which case your teachers are very, very special people. Okay, so tonight in the stream, you can find all the resources that we're going to be using on my GCSE website. All you need to do is go to gcsephysicsonline.com. And when you go there, you'll see this little icon, which is the live button. If you click on that, it takes you to this page. This is basically the timetable for lives. For the 17th, if you just click on the date, it brings you up what we're doing. We're going to be doing some stuff about energy and also specific heat capacity. So I think energy is generally okay. Specific heat capacity is a little bit harder, but I've got some questions from that. Now, the questions you can find... Well, that's a weird noise there. You can find the questions by basically downloading this set of practice papers. And so if you click on this or you click on download, you can download all of the past papers. Now, if you're not sure what they entail, again, on my website, and this is again a kind of shameless plug to say, please buy this. I know this will help you get the grades that you want. If you click on where it says practice papers, I've written a set of 12 papers, 6 for paper 1, 6 for paper 2, based on the AQA triple science, which is what most of you are doing. And basically there's information about them on the website. And if you want to, which I think, there's no harm in doing, it's completely free to do this. You can download a sample paper and that shows you the style of questions. And there are a lot of the ones that we've been doing this week. Loads of questions there, loads of information. So if you want to buy these practice papers, have a look on the website. So we're going to start with a question, which is what you want, isn't it? You want some proper physics. Good. People are talking already about buying the daily workout books, which are more for A-level, but perfect for if you're doing A-level physics after GCSE. Okay, so the first question is about a bouncy ball. It's dropped from rest, and then it bounces up and down multiple times. So what we have here, if this is a height above ground, well, another way of thinking about this is that's going to be the distance above the ground, s, and we've got time t along the bottom. So all we have here really is a distance time graph. And so what we can see is that as time goes on, the distance above the ground gets smaller. It then bounces up into the air and then it bounces again and again and again and again. So this is the kind of thing that you probably will be familiar with. Okay, it's recorded using a distance sensor and a data logger. So this gives us lots of data and it shows how the ball's height varies with time. Now the first one, we need to describe the changes in the way that energy is stored in the system as the ball goes from the point labelled A to B to C. Okay, so what we're thinking about here is the way that energy is stored. And I think that there are basically 3 main energy stores here. So we've got people talking about gravitational potential energy, people talking about kinetic energy, but there's another store as well. But what I'm going to do, just to sort of kind of make this simple, is I'm going to think about position A, position B, and position C. Okay, and we're going to think about the amount. I'm going to call it GPE. We're going to think about KE to represent the kinetic energy, and also we've got thermal energy as well. Okay, sometimes called internal, but I think thermal is a much better one. Okay, so basically at A, at this point here, the ball is not moving because it's held at rest. So the kinetic energy is 0. And what we have at this point is the maximum amount of kinetic energy. And by the way, everybody in the chat is awesome. That I can see kind of out the corner of my eye as I'm kind of doing this, that people have got some really, really good explanations. Okay, and it doesn't matter if you're wrong in the chat. Nobody cares. You don't necessarily know who these other people are. You won't recognise them from school. So it doesn't matter if you make small mistakes. So we've got the maximum kinetic energy, 0 kinetic energy, and at this point we've got 0 increase in the thermal energy. Okay, now as the ball accelerates towards the floor, This is because, and I'm just going to draw the ball up here, there's going to be a force acting on it. Now, for those of you who were in the stream yesterday, what's the force acting down on this object with mass? Okay. So, what is the name of the force acting down? And this is something we did in the live stream yesterday. Hopefully, some of you might have been in it. Weight, Wilf, yes, excellent. Free maths lessons, weight. Angus, weight. Yes, so we have the weight force down. And basically, this weight is going to be the resultant force on that object, or it's going to be the thing that kind of causes it to accelerate. And as the weight is acting down, we've got a force acting over a distance, and therefore what we have is mechanical work. Okay, remembering, of course, that the work done is equal to the force times the distance moved in the direction of that force. So the energy transfer process between these stores, in this case, is mechanical work. We've got a force acting over a distance. Now at point B, it's accelerated, and we could actually work out the size of this kinetic energy, because that would just be equal to a half mv squared. Of course, at the top, the GPE would be equal to mgh. Okay, and these are equations that are given to you, but it's always, you know, for this one here, I think it's just nice to sort of write down how we could actually calculate the size of those things. Now at B, what we have is zero potential energy relative to like this kind of start point. So when we're looking at potential energy, what we're really looking at is the change in potential energy. Sometimes we put a triangle in front of it, which is delta, that just means change in, because that object would still have kinetic energy, would still have potential energy at this point, but what we're looking at is the change in potential energy over that height. Right, somebody says, can I make a video on how to flex on GCSE physics? I don't need to, I've already got loads of videos. You just need to watch me and then you'll be absolutely fine. Okay, at the bottom though, we're going to have the maximum kinetic energy, but there will also be a very small amount of thermal energy. And that's because as this ball is going towards the ground, as it gets faster and faster, there's going to be air resistance. There's going to be a very small drag force. So I'm just going to put this force kind of acting up. And the size of that drag force is going to change, and it depends on how quickly it's moving. But again, we have a force acting over a distance, and therefore we're going to have some work being done on that object, and therefore energy is transferred to the thermal store. Now at C, we have the ball bouncing up. You can see at this point here, when the curve gets to the top, what's the gradient of the line at C? Catherine W, if you ignore air resistance, would all the GPE be transferred to the KE between A and B? No, it wouldn't. Okay, because the thermal store that increases is going to be the thermal store of the air, which is due to the drag force, and also there's going to be some thermal store of the ball because it's been squashed, because it's a bouncy ball, and also there's going to be the thermal store of the floor. Okay, so as this is bouncing, there's going to be some energy losses here, and so the ball heats up, the floor heats up, and there's going to be a very small amount of heating in the air. Okay, right, so yeah, tangent drawn to the line. So if we were to actually kind of work out the gradient here, we draw a tangent to the line, which in this case, and this is quite a tricky thing, and this is very much a higher tier only kind of skill in physics, but of course I'm sure you've seen it in maths. If you were to draw a tangent to that line, we'd find that the gradient is 0. And that's because the change in distance over time is 0, because its velocity is 0, and that's because the gradient is equal to 0 at this point over here. So if the gradient is 0, there's no velocity, therefore the kinetic energy must be 0 at C. The GPE, there's going to be some GPE, and I guess you could always kind of look at how much that proportion is of this initial amount just by looking at the graphs. You can sort of look at that, and there will still be a thermal store of the surroundings. So there's still going to be the thermal store of the air, the ball, and the floor. Now, something else you might notice with this graph here is that each time it bounces up, it doesn't quite go as high, and it tends to lose the same proportion of energy each time. And because it's not going as high, it's not going to be in the air for as long, so the time decreases each time. And if you get a ball and you drop it, you'll notice that as it bounces, it goes bounce, 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 bounce. Okay, it sounds a bit like this. So it bounces, and then... So what you hear is that sound getting closer together. Somebody asked about sound energy. There is no sound energy as a store. Okay. Instead, what's happening is that if you do hear a sound, that's just the way that the energy is being dissipated into the thermal store. Okay. So what we have is mechanical work is the energy transfer process. So we're having mechanical work as we go from gravitational to kinetic and back to gravitational. There might be a small amount of sound, which is kind of the way that energy is radiated away into the thermal store of the ball and the floor, maybe. Okay, and yeah, it's because the dissipation of energy, this is what actually causes the ball to bounce lower each time. Okay, I actually saw a really good video on TikTok. I think one night, you know, and I probably should have been sleeping, I was just scrolling through TikTok. It served me up physics stuff. And they had, I think they called it the atomic trampoline. And they had a ball that bounced, and it kind of basically went about 95% of the height of the initial drop. And that was a really nice demonstration of the way that the metal or the actual atoms within the lattice were structured. But that was called the atomic trampoline. So you might want to kind of Google that or look on TikTok after this. Okay, so the first question about energy stores and transfers. Right, we then have some data. So this is what I said yesterday. When you see a question, maybe read through the whole thing. So we've got the mass of the ball, it's dropped from this height. What's the maximum possible velocity of the ball before it hits the ground for the first time? So if we know, or we can work out the gravitational potential energy here, and we assume that's all transferred to the kinetic energy, what's going to be the speed as it hits the ground? Okay, so I would say we've got a mass, we've got the height, and we want to know the velocity v of the ball before it hits the ground for the first time. Now there's two ways that you can do this. Okay, I'm going to show you the first way, the easy way, and then the second way, which is the proper physics way of doing it. So the first thing is we could work out the gravitational potential energy as being equal to mgh. Now I remember that, but I would just go and check that in the formula booklet. I can see lots of people, and I know that some people love it. Some people are kind of writing down stuff, and I think this is really helpful actually. So that's going to be equal to 0.30. I'm going to use 9.8. Now I think some exam boards use 10. I think Edexcel tend to use 10. I'm going to use 9.8 as my value for G. And we're going to multiply that by the height, which is 3.6. I know people have worked it out for me, but I'm just going to check. So 0.3 times 9.8 times 3.6 is 10.582. I'm going to leave that number like that. The next thing is we know the kinetic energy is equal to a half mv squared. Now you could either substitute the number in and then, so you can put the numbers in and then rearrange. I'm going to rearrange this to say that v is equal to 2 times the kinetic energy divided by the mass square rooted. Okay, so what I did was I multiplied both sides by 2, divided by m, and then square rooted to get v. So this is the skill that you should have by now. So v is going to be equal to 2 times 10.582 divided by 0.30 square rooted, and I've just written down the whole number that we had up there. Okay, so going to multiply that by 2 divided by 0.3, square root that to find that v is equal to 8.4 meters per second. Okay, now that is a good way of doing it. Okay, and I know lots of people have written down the right things over here. I'm going to show you another way which I think is better, but it's a bit more risky. We know that, or we're going to assume that there's no air resistance, and therefore we can say that this initial gravitational potential energy is going to be equal to the kinetic energy after it's dropped. Now that's equal to mgh, and that's equal to a half mv squared. And what we can see over here is that we've got an m on both sides of the equation. So we can cancel those, which means we don't even need to know how heavy that thing was in the first place. We can then say that GH is equal to a half v squared, and then I can multiply both sides by 2 and square root to say that v is equal to the square root of 2GH. Now, therefore, this is an easier approach, and that means we could just work out the final velocity just by saying we've got 2 times 9.8 times 3.6. We square root that, and when you do that, again, you'd find the answer is 8.4 meters per second. Okay, I think that people here are asking some good questions. You don't need to round down until the very last answer. So what I wouldn't do is round that down to like 10.6 or even just 11. I would use all of the numbers in your kind of intermediate calculations and only round down at the very end. Okay, so this is more kind of like an A-level method, but at GCSE, it doesn't matter which way you do it. I would say that if you're not super confident, work out the potential energy and then equate that to the kinetic energy and do it like this. But you can see that this thing here means although there's a bit more manipulation with the formula, it's actually easier to do the maths because there's less mistakes that you might make. Okay, it's also, for anybody out there who's been doing SUVAT equations, I'll just put this as an aside. If you've been looking at S, U, V, A and T in maths, now the height, the distance it drops is h, the initial velocity is 0, the final velocity I'm just going to call v, the acceleration is g, and it falls for a time of t. Okay, now there is an equation that says v squared equals u squared plus 2as. But of course, if u is just 0, we kind of cancel that. And therefore, we could say that v is equal to the square root of 2as, but a is equal to g, and s is equal to h. So we could also write this as v is equal to the square root of 2gh, which is exactly the same equation as we have over here. Okay, but you don't need to know that for GCSE. Right, so here we go. Let's have a look at this question here. I'm kind of running over time. I just keep... No, I think we'll have enough time. Okay, we've now got a separate experiment, which is 4.3. Can you just put down H, M, R, or E? Okay, so H for heating, M for mechanical, R for radiation, which could be light or sound or electrical work. Okay, so the ball is put in an elasticated catapult, which is level with the ground. The catapult is kind of pulled back and used to project the ball forwards. And basically, the energy is transferred from the elastic potential energy store to the kinetic store. So if you get a question like this, loads of text, the thing I'd do is basically, well, here's my kind of fixed points, here's the ball, and basically it's in this kind of catapult like this, it's pulled back over here, and then a small amount of time later, that's kind of left and that just goes sort of limp. The ball is then projected forward. So sometimes drawing your own diagram just for your own sake is useful. Everybody is awesome tonight. Humphrey, Sapsart, Nathan, Catherine, me, Therapy Gaming. Good to see a lot of people back again. Ling Ling, Angus, yeah, Pancake Man 2K, free math lessons. Yeah, mechanical working. And the reason it's mechanical working is because what we have is a force, in this case provided by that rubber, acting over a distance. So we've got a force times a distance, and therefore we have work done on that object. Okay, and also in that, none of the other options would make logical sense. Catherine, yeah, that's sometimes right. Sometimes you don't just have to know the physics, sometimes you just have to think, well, if this is an elastic band causing a ball to go forwards, there's no heating involved, there's nothing electrical, and there's no like light or sound really. So I think sometimes common sense is actually going to carry you really well through the exam. Okay, right, the next question, this one over here, describe what is meant by the internal energy of a substance. Okay, so this one over here is a bit of a more kind of tricky topic. And actually, this is kind of covered again at A level, but they make it even more interesting because you do like gas laws and stuff like that. Okay, now what I'm going to do is write this down as simple as possible. Okay, Brockles, great stuff. Basically, it's going to be the sum of all of the kinetic plus potential energies of the particles or molecules in a system. Okay, now this kind of crazy letter, it looks like an M on its side or like a capital E. This basically means the sum of. Okay, now you don't need to know this for GCSE, but again, I want you to be better than GCSE. I want you to be kind of understanding the kind of sort of the physics and the way that maths can be used. So basically this says the sum of the kinetic energies and the sum of all the potential energies of all the particles in a system. Okay, within an object, within a system, sometimes you can use the word molecules. Yeah, so all of these things over here. And I think total kinetic energy and potential energy of an object, Zeno, yeah, that's fine. Here we go. Yeah, lots of great stuff there. Again, something like this, it's a 1-mark question. You can write this down in 30 seconds because this is just knowledge. It's just a fact you need to remember. Again, I did kind of show this yesterday. I showed this free revision guide that I've got. I think in the back, I've got the definitions that you need for AQA somewhere. So here are the definitions. Do I have internal energy? Yeah. So this is what, as far as I can see, AQA say. Internal energy is the total kinetic and potential energies of all the particles that make up a system. Okay, that's the kind of thing you need on a key card. That's the kind of thing that you can basically, you know, just have in your pocket and just look through it. Right. How to get this revision guide, free maths lessons. All you need to do is, I'm going to keep saying this, but basically go to GCSE Physics Online, go to my website and spend half an hour playing around. There's lots of stuff out there. So basically from the home page, because this guide I made was mainly for AQA, choose the AQA exam board. And then along the top it says free digital download for AQA GCSE revision guide. Click on that, enter your email, and it'll just get emailed to you automatically. So this is something that's completely free. Okay, Ling Ling, thanks so much. Appreciate that. Yeah, somebody's talking about CGP. They are pretty big. I use CGP, it helped me a lot. Okay, so that's internal energy. Right, we then have a kind of scenario. We've got a cyclist going a long way. They want to keep the water cool inside the bottle. And what they do is they basically freeze the water inside. And again, in your exam, you can add whatever you want onto your diagrams to make it useful to you. Okay, so here we go. We're going to freeze the water inside. So we've basically, I probably should say frozen water. And that just reminds me that's what it is. Okay, now outside is going to be warmer. And that means we'd have a transfer of energy from the warmer to the cooler place. So I'm just going to put an arrow here to show that basically this is how energy is being transferred in this situation. Okay, now these are just kind of my notes for me. Okay, why is it important the thermal conductivity of the bottle is low? Now this question is really about what do we mean by thermal conductivity. Effectively, that's how good something is at conducting heat. Okay, and actually, Catherine, you've put a brilliant answer there. A low thermal conductivity will prevent heat from being conducted to the drink, which could warm it up. Now, of course, it's low, so it's not going to completely stop that thermal energy transfer. And I think it's better to use the word thermal energy rather than heat. And basically what this is going to do is just going to reduce the rate of that energy being transferred. So you might say something like, so there is a lower rate of thermal energy transfer. And the reason that's important, and this is the explanation bit here, is this means, so the drink stays cooler for longer. Okay, so the reason we want to reduce that rate of heat transfer is because we want that cool bottle of water to be as cool as possible for as long as possible. Yeah, there's some great stuff here, Nathan, Zeno. Yeah, I think there's some really good answers there. Good, right. The next one, this is a big question, and it's about two things. Although I said specific latent heat, we're going to be looking at the specific latent heat of fusion of ice. So this, anything to do with the word latent is to do with a phase change, or basically we're changing the phase from maybe a solid to a liquid or a liquid to a gas. So that's what we mean by this. Okay, now, we've got lots of information here. So they freeze 700 grams of water. So it's turned to ice and is at a temperature of 0 degrees when they start the ride. We then have a time of 1.5 hours. The average rate at which the drink absorbs energy from the surroundings is 50 joules per second. So that's how much energy is transferred every second. We then need to calculate our answer to two significant figures. So how hot, or what will be the temperature after that amount of time? Now this question here is harder than anything at GCSE. I guarantee if you can do this question or get a couple of marks here, you're doing better than most people. And this question is probably one of the hardest topics, and I've given you a really hard question because that's the way to do things. Okay, now, what do we know? We know the time, and we know how much energy it absorbs from the energy. We know how much energy it absorbs every second, which is what we call power. So basically 50 joules a second is the same as 50 watts, and that's equal to the power. So how do we work out all of the energy transferred? Well, we know that power is equal to energy per unit time. So the energy is going to be equal to the power multiplied by the time. So effectively what we're saying is there's going to be 50 joules of energy transferred per second. And what's the time? Well, the time is 1.5 hours. So I'm going to multiply that by 1.5 hours. And then I'm going to multiply by 60 minutes and by 60 seconds. Okay, so all of this here is the time. And you must never forget that you have time in seconds. So if I work this out, that's just equal to 50 times 1.5 times 60 times 60, which is equal to 270,000 joules. Okay, so that's all of the energy. Okay, now I suspect I'm going to go slightly beyond into the A-level territory, which normally starts at about 8. So if you're an A-level student who's joining for the stream, I'm sure all of you can do this as well. Did I get that right? 50 times 1.5. Okay, so I think that's all good. Right, now the next thing is that this total amount of energy transferred is going to be equal to the energy that melts the ice plus the energy that then starts to warm up that water. Okay, so for the specific latent heat of fusion, I'm going to do this in this kind of blue colour. Now here we know that the energy transferred is equal to mL. Okay, so the mass times the latent heat. So this is going to be equal to mL, but also some of the energy is going to cause the water to heat up, which I'm going to be doing in red. And so that's equal, so we're going to add this, to the energy that causes it to increase in temperature. And we know that this energy is equal to mc delta theta. So mc delta theta. Okay. Would I recommend taking A-level physics? Yes, I would. I think there's going to be some other people maybe stressing a bit at the moment who might be saying no. So ignore anybody who says no. But yeah, A-level physics, definitely the best A-level to take. Now we're going to put some numbers in. Okay, the change in energy, we've just worked it out up here as 270,000 joules. Do we know the mass of water? Well, we do, because it's just 700 grams. And so the mass here is going to be 0.700 of a kilogram. Okay, do we know the latent heat? Yes, it's actually 336,000. Okay, so this is going to be all of the energy that causes the ice to melt, plus we've got again the mass, which is 0.700 kilograms. We're going to multiply that by the specific heat capacity of water. This will always be given to you. You don't have to remember this, but you should recognise when you do a few questions, it's normally about 4,180 or 4,200. And that's multiplied by delta theta. Now this is a change in temperature, and this in the question is the unknown thing. So what I would say is I'm going to work out what's over here. So we've got 0.7 times 336,000, which is, so 270,000 is equal to 235,200 plus, we've now got this number over here, so 0.7 times 4200, which is 2940, multiplied by the change in temperature. So that's our energy to melt the water or the ice, and that's the energy which has been transferred to that liquid water, which is now increasing. Okay, is this still GCSE? I reckon it is. I reckon this is a very hard GCSE question. But if you're A-level, then yeah. Why am I not writing the units? I only write the units at the very end. Okay, so I'm not going to write the units as part of my calculation. I only need to write the units at the very, very end when I'm going to give my final answer. Okay, hopefully that helps, Bleach. Right. So we can then say that 270,000 minus 235,200 divided by 2,940 is equal to our change in temperature. So let's see. This gives me a change in temperature of 11.8 degrees Celsius. But of course, we want to round this up to two significant figures, like it says in the answer, and therefore that two significant figures is just equal to 12. Okay, now this is, I reckon, harder than anything at GCSE. However, this is just relying on GCSE knowledge to answer it. Okay, and of course, a lot of you are really happy that you've got the, oh, hold on. Yeah, it's going to be 12 degrees because it starts at 0. Okay, yeah, I think a lot of you for GCSE are really fortunate you have the equation sheet. It means you can just double check the things, and that means you, when you're in like kind of a stressful exam situation, if you're not quite sure about something, rather than losing lots of marks, you can just double check that you're on the right track. Okay, the first part of finding power was hard, yeah. But I reckon it's kind of like, if we know that there's 50 joules a second, and we know there's 1.5 hours, then 50 joules a second times the time in hours gives us the total energy transferred. And that was 6 marks, though. That was a 6-mark question. Of course, if you do want to actually buy the practice papers, they actually come with the questions, but they also come with a mark scheme, and they come with a set of model answers as well, with extra kind of notes and things. And of course, everything is supported by a video. So you can basically buy, again, this is like the kind of sort of shameless plug thing, but basically if you buy these GCSE practice papers, there are 12 of them in total. They come with the question paper, the mark scheme, a set of work solutions. It's all digital. And on my website, if you've got a premium plan or a school subscription, there's then a video where I explain every single answer as well. That's basically 120 GCSE questions. Okay, right. That is it for GCSE. Thank you very much for everybody who's been so far. Ling Ling, Angus, Nathan, so many people whose names keep coming up. Yeah, right. Catherine as well. Okay, so now we're going to be doing A-level physics. So tonight for A-level, and again, to everybody doing GCSE, let me just show you what we're doing. So for A-level tonight, again, you can find the kind of schedule of what we're doing. You can download the resources completely for free. I'm doing this for free, but if you do like what I've been doing, and you know that there's actually a lot of stuff on my A-level website, You can buy a premium plan, so you can access all the videos. You can buy books, you can buy past or kind of practice exam papers. But tonight, the live stream, the one we're doing tonight is the 17th. And we're going to be looking at a question about IV characteristics and kind of practical work. Yesterday, a lot of people said they wanted to do some electrical questions, so we're going to do that today. And these are based on questions from the Daily Workout Book 3, which if you're in year 12, a lot of people are now buying this. I've seen like a big uptake in sales. So this book here basically will help you revise everything for year 12 and set you up really well for year 13. The questions that we're doing are from the 11th and 12th of May. Okay, so there's, well, that's March, 11th and 12th of May. So we've got some questions here about IV characteristics and so on. So we're going to talk through those for the rest of the stream. If you want to just download the questions only, just click on download now, and then you've got the PDF that has the questions we're going to be doing tonight. And of course, if you want to see what we're doing tomorrow, you can download the questions for tomorrow, which is more about like a year 13 style kind of question. Okay, right. Animated Science has been plugging your content at my school so much. Awesome. Right. What's the best way to learn about a topic? Just do past papers. That is my biggest thing now, is do as many questions as possible. If you want to, if there's one particular topic that you need help with, there's some good stuff over at Physics and Maths Tutor. They've got questions split up by topic. You've got Isaac Physics, loads of good stuff out there. Would the books be helpful for a year 13 revising year 12 stuff? James. Yeah, I'm going to say that, to be honest, I think at this point, if you're year 13, it's better to do the past papers. I think if you want to buy the book, it would definitely help you revise all the year 12 practical stuff. But if you really, but I think it's almost like, because you've only got a couple of months left now, I'd say don't buy the book if you're in year 13. Instead, maybe just do as many past papers as possible. Okay, right. A student is investigating the current voltage characteristics of a filament bulb. So what I think is we're going to have something that's going to look probably like this. Okay, all of you know the IV shapes. Okay, use the data in the table to calculate the resistance when the PD is 4 volts. Okay, so here the resistance is just equal to V over I. Okay, the resistance of something is defined as the potential difference across it divided by the current through it. That is the way that resistance is defined. Okay, now for the first one, this is just going to be equal to 4 volts. And when there's a voltage of 4, or potential difference of 4, we're going to divide that by the current of 1.05. Which gives me an answer equal to 3.8095. So that's about 3.8 ohms. Okay, that's all it is. 3 maths lessons, 3.8, perfect. Should you give your answers to 2 significant figures? Yes, you should, because that is given to 2 significant figures. So we can only justifiably give our answer to 2 significant figures. And here's the thing about significant figures and decimal places, and this is the kind of the quirk of how we teach things. If you look at the current, we're measuring something to 2 decimal places. So this looks like it's 2 significant figures, but even though it's the same measuring device, and we're still measuring to the same number of decimal places, this is now 3 significant figures, 3 significant figures, 3 significant figures, and 3. But the PD in all of these cases, I know what people are going to say now. Basically, the PD has been measured to 2 significant figures. So for the second one, R is going to be equal to V over I, which is 8.0 divided by 1.65, which is equal to 4.8 ohms. Now the last one, did I make a mistake in my book? I said the last one was equal to 10.0 divided by 1.85, which is 5.41. Okay, really, I suppose I should give that to 3 significant figures because that's 3 significant figures, and so's that. So really, this last answer should be 5.41. But this is the quirk about the way that when you actually take real data, But ultimately, it doesn't really matter because as soon as we start to plot the data on a graph, what we find is that we can't really plot to the nearest 0.01. So I reckon 5.4 is fine. Okay, what we then need to do is plot the results onto the axis provided, or the axes. So I'm going to say that's 0 because we start at 0. The potential difference goes up to 10. So I reckon that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and that's going to be the potential difference measured in volts. Right, shouldn't I be on the x-axis? By convention, it doesn't really matter, really. I mean, normally they're referred to as an IV graph, or the IV characteristic of a component, because by convention we tend to measure or plot current up here and potential difference across there. But I do remember and a lot of people will have seen this, sorry about that. These questions, by the way, are completely free to download from the A-Level website. Yeah. Now, the questions are part of a book, so if you want to buy the full book, you have to pay for that because it's a physical product. But if you order it today, it takes a couple of days to come from some big Amazon warehouse. But yeah, you do buy a book and it's got 4 months worth of questions or just a huge amount of stuff inside it. So you can see there's lots of stuff there that you can use. But I do remember when I saw some questions from Isaac Physics, they had questions, where was it? I'm sure all of you have seen this. It'll be something to around 22 maybe, or was it in the GCSE book? Maybe it was a GCSE book, they had this question. Okay, no, it's not in there. Maybe it's in the GCSE book. They had a question where they had a VI graph, and they basically had something plotted like this, and it showed a kind of sort of curving upwards things for a bulb, which kind of confused lots of people. Okay, so we're going to have V across the bottom, I up the side. This goes up to almost 2, so we're going to have, okay, that's 1.0, that's 2.0. So the numbers are going to be like 0.2, 0.4, 0.6, 0.8, 1.2, 1.4, 1.6, 1.8. Okay, so just kind of simple axis, and this means really it doesn't really matter if we've got something to 3 significant figures, because we can only really give something to about 2 significant figures maybe. Okay, plot the results on the axes provided. So we've got 0, 0, we've got 2, and we've got 0.6, 4, and we've got 1.05, which is going to be about here, roughly. 6 is going to be 1.4, 8 is going to be 1.65, and then 10 is going to be 1.85. Okay, so what we have here is something that shows that as we have a greater potential difference, we have a greater current in that circuit. Now, when you actually look at this with the ruler, you can see, because it has to go through the origin, we definitely don't have a straight line. Instead, what we have is a curved shape. And the best way to do this is with a pencil, and keep your hand on the inside. We're going to get a shape that looks a bit like that. It's a little bit wobbly, I'm afraid. There we go. So basically, that line's not brilliant, but I guess if I wanted to, I could just like rub out the end and just do that a bit better. What do you draw to plot the points? I just tend to use a little cross thing. Right. Calculate 1 over the gradient at 8.0 volts. Compare this to the value for part 2 over here. So we're going to calculate the gradient at this point over here. Now, to work out the gradient, what I'm going to do is draw a tangent to that line, which is something a bit like this. Okay, so here is, again, this is just a rough thing I'm doing while I'm doing the live stream. If you're in an exam and you have to draw a tangent, there's often a fair amount of leeway in terms of the actual line that you draw. Okay, Right, so to work out that tangent, the most important thing is that you need to draw a big triangle, which is what I said yesterday. And you're going to draw that triangle up to the line. Okay, and we're going to use this then to work out the gradient. So the gradient is going to be the change in y value, which, looking at this, I reckon that's about 1.9 take away 0.8. So that's going to be my change in y value. And the change in x value is going to be equal to 10 minus 0, which is then equal to 1.1 over 10. So that's 0.11. Okay. Right. What are people saying in the chat? So yeah, this is a good point, Catherine. Yeah, so I'm going to talk about this now. So the gradient is 0.11. Okay, so I'm just going to write this down here. The gradient is 0.11. Now we're going to take the reciprocal of that. So 1 over the gradient is going to be equal to 1 over 0.11, which is equal to 9.1. Okay, so 1 over the gradient is equal to 9.1, but the value that we had for the resistance at 8 volts was actually equal here as 4.8 ohms. Okay, so what we can see here is that 1 over the gradient is not equal to the resistance. And that's a really, really important thing. Okay, is this GCSE? I reckon it's based on GCSE knowledge, but in an A-level context. Kind of doing this kind of stuff here, it would, I think, probably cause mass panic if it was set in a real GCSE exam. Okay, so yeah, basically, when you have an IV graph, 1 over the gradient is not the resistance at that particular point. If you want to work out the resistance, what you're doing is looking at the ratio of 8 to 1.65, but that's not the same as 1 over the gradient of that line. Hopefully that's clear, and that's a really important thing to remember. Right, we're going to do something fairly similar for the 12th of May. This one is a diode. Again, it's connected up in a very kind of sort of similar circuit, but I'm just going to draw on the other side, the circuit that you might use. Okay, you're going to have some kind of variable power supply. You're going to have an ammeter. You're then going to have your diode. You're going to have a resistor, and then you might have maybe either like a variable resistor in the circuit, or you might just have a dial that allows you to adjust that power supply. So basically this is our circuit, and you only put the voltmeter in parallel with the diode. Okay, because you only want to measure the potential difference across the diode. What lots of people do is they put the potential difference, they measure the potential difference across the diode and the resistor. Okay, now the resistor is basically designed to limit the current when this is connected the right way around the circuit. Because if you didn't have a resistor here and this was connected up in the right way, it would have a low resistance, and that means you'd have a massive current in that circuit, and that would just cause this to melt. And at the moment, this is for anybody doing A-level physics. I reckon everybody needs to know about diodes and the IV characteristics at A-level. So this is suitable for AQA, EdXL, OCR, international A-levels as well. Right, the first thing we're going to do is we're just going to plot the data. Okay, we can see that the maximum value for the current in milliamps is 80, and so luckily this fits on rather nicely. So we've got 20, 40, 60 and 80, and that's at 0 down there. Now the potential difference along here, we basically go from minus 0.5 to plus 0.75, so let's say that's minus 0.6, minus 0.4, minus 0.20, and then we've got, hopefully this is all making sense, 0.2, 0.4, 0.6, 0.8, 1.0. Okay, And I think, yeah, this does, the Basilisk, yeah, this does cover CIE and Edexcel International A-Level. It's just a standard practical. So the first thing we're going to do is just record that data. So we've basically got 0, 0, 0, 0. Then we've got at 0.5, it goes to 1. At 0.6, it goes to 3. 0.64, which is going to be around here somewhere, it goes up to 6. 0.68, it goes to 22. 0.7, it goes up to 40. And 0.72, it's up at 80. So basically, this is what we have: 0, 0, 0. And then over a very small range of potential differences, we go up to a massive value. Okay. Yeah. And I think at the moment, this is still a topic covered in AS physics. So I'm just going to put my hand here, going to draw that line down. I guess that then goes down to 0. I'm going to continue that with my ruler. Okay, that's basically just going along there. So this is kind of the thing that we see with the diode. Again, this isn't any different to what you'll have done at GCSE, but the actual practical is really difficult because you've only got like a really narrow kind of point where you can measure the potential difference, and we get a massive change. Okay, Vapor asking a good question. Does 1 over the gradient equal the resistance if it's an ohmic conductor? Yes, it does. Okay. So in the last question, we were looking at this filament lamp. Okay, here, 1 over the gradient is not equal to the resistance. Here, 1 over the gradient isn't equal to the resistance. This is only that's only true if you have an ohmic conductor. Okay, but yeah, that's like the kind of the exception, I guess, that proves the rule, if that's really a thing. Okay, calculate the resistance of the diode at 0.6 volts. So again, R is equal to V over I. At 0.6, the resistance is going to be 0.6 divided by the current of 3.0, and that's just going to be equal to, no it's not, it's 3.0 times 10 to the minus 3. Always look, and maybe sometimes it's worth like underlining or highlighting if you've got some weird unit. So we've got 3 times 10 to the minus 3, so 0.6 divided by 3 times 10 to the minus 3 is equal to 200. So a pretty high resistance at that value. At 0.7, we've got R being equal to V over I, which is now 0.70 divided by 40 times 10 to the minus 3, and that's equal to, is that 40? Yeah, so 17.5, which is 18, isn't it? So what we can see is that just with a very, very small increase in potential difference, the resistance drops massively. And if we were to look again at maybe the next point over here, we then have 0.72 divided by 80 times 10 to the minus 3, and then it goes down to 9. So what we see is we have a rapid drop in resistance over a very small range of potential differences. Right, this is something that you can't answer in the chat. How could a diode be used in half wave and full wave rectification for an AC supply, and sketch a graph of PD against time for these two uses? Okay, so this question here is something that I've put in a book for AS students. Now, all you need to do is go to something like ChatGPT or go to Google or even probably TikTok, I no doubt now, and basically you can just do your own research. Okay, there's two sorts of things where we can either use half wave or full wave. Okay, and this is basically for an AC supply to turn it into a DC supply. Okay, now alternating current is where the electrons are going to be moving side to side, but they're still transferring energy around that circuit. And if you've got half-wave rectification, effectively what we start with is our AC signal, which looks a bit like this. Okay, so we have this AC sinusoidal wave. And basically, when the current is going one way around the circuit, the diode lets it through. But when it's going in the other direction, because we've got a diode in that circuit, it basically stops the current. And that means what you'd have is you'd have maybe a positive value and then 0, and then a positive value and then 0, and so on. Okay, so that's what you'd actually see. We only see the direct current, but it's a changing direct current. Now for a full wave, what we do is we basically, again, start with this AC signal, and we still have some diodes in that circuit. And basically they let the current go through when it's going in one direction, which is fine. But when the current is going in the other direction, they basically flip it over to make the negative current positive. And then what we get is a current that looks like this. So it goes up to a max and goes back to 0, maximum to 0, maximum to 0, maximum to 0. So effectively what we've done is we've flipped all of these negative bits around to make them positive. And this is called rectification. And what we do is we rectify the signal and turn it from an AC signal into a DC one. Okay, and then of course what we can also do is you can have a capacitor in that circuit, and we then kind of smooth out the signal, because every time it gets to a positive value, rather than dropping down to 0, it basically drops down again, meets here and it drops down, and what we then get is basically a signal which looks more like a normal DC thing. What was that equation to convert from AC to DC? I don't think there's an equation that you necessarily need to know at A level. This is maybe kind of covered by a few exam boards in year kind of 13 topics, but there's not actually an equation for that. I guess really it would be something like potential difference is going to be equal to 2 pi f or something, is it? Something like that, and it's just going to be there'll be something, I can't remember what it would be. Okay, right, do we have any questions for the last few minutes? Gisket says, is there any data on which questions come up most frequently? There is data, I don't have it though, and I haven't done an analysis of all the questions that come up most frequently. However, I would say if you want to do well in your exams coming up, try not to just think about what are the predicted questions, or if it's been asked 2 years ago, it's definitely not going to come up again. I think, and from what I've seen with all the students I've ever taught, the people who do well are good at everything in physics. So they've got a good broad set of skills, and they practice full past papers, and they basically do all the questions, including stuff that's come up last year or the year before that. Right. How do you get those calculator settings so that multiple calculations are displayed at once? All right, I made a video about this, I think. So basically, I'm hoping I don't mess this up now. When you go to, so this is the Casio FX991EX class whiz. If you go Shift and Setup, I think it's Input Output 1, and then you just want to choose one of these. And I think it's line 1 input, line 1 output, I think. But I would say with your calculator, just go and play around. So just go to Shift Settings, go to Input Output, which is number 1, and then just go through those one at a time to see which one works for you. Okay, hopefully that makes sense. So this was the third live stream. I'm going to be doing live streams 4 or 5 days a week. If you want to find out what I'm up to next, then head over to alevelphysicsonline.com/live. You can see what I'm doing tomorrow. You can download the questions, which happen to come from Book 4. I think the question, I can't remember the date, but I think it's the 11th of July, maybe. It's on my website. I put it in earlier. Yeah, it's a question about specific heat capacity, quite similar really to what we did with the GCSE part of the live stream earlier. But I'm going to be basically doing live streams every single day. Some of them are going to be questions from the book. I'm going to be doing some past papers, some practice papers. Basically, we've got about, I think, 2 months ahead of us. I think your last paper 3 physics A-level exam is in about 60 days' time. So we've got plenty of time. And my hope is to hopefully get all of you from wherever you are at the moment up to the highest level. Okay. Will I be going over some questions on turning points at any point? That's a good question, Rasan. Maybe. Because, actually, I do have something that I'll show you tomorrow. But basically, for those of you who've gone to... Right. This is basically kind of the end of the live stream, but I'm just going to find something that will help you if you're doing AQA turning points. Let me just find it on the iPad. It's worth waiting. If you're doing AQA and you're in year 13 and you're doing turning points, I've got something which is amazing to show you. And it took me ages to do. I did it earlier this year. Right, I just need to log in. So basically on my website, you'll find on the main page there's stuff down here, and one of them is that I do have work solutions to PMT multiple choice questions by topic. Now you can click on that, you can just find it in the footer. Let me just enter my password. Sorry about this silence. It's very hard to do 2 things on a live stream. Okay, so basically, this is worth waiting for, okay? I do have on the Physics and Maths Tutor website work solutions to all of the AQA multiple choice questions, but I've also got them hosted on my website, so it's easy to find. And I've basically got a page which is, I think the URL is PMT-solutions, but basically on this page I've got all of the multiple choice questions that Physics and Maths Tutor have got, and also they've got questions for turning points. So if you look at the bottom of the page, what you'll find is for the different sections 1, 2 and 3, I've got my work solutions to the Physics and Maths Tutor questions on turning points. So here's the stuff on wave particle duality, here's the question, and so I just scroll down a bit because some of them are repeated. Here we go. So here's a question about diffraction, and here's a work solution. So you can actually see how to work out the answers, something about electron diffraction there, multiple choice things, there's some like lensing. There's basically lots and lots and lots of answers, all with full work solutions. So if you're not sure about things, there's basically all of that on my website. So that's the one on wave particle duality. I think there's another one on the last bit, which I think gets quite tricky. These are special relativity, so I've got my work solutions to special relativity questions. Again, these are the ones that you can find on the Physics and Maths Tutor site, but I've got some work solutions done in collaboration with Physics and Maths Tutor. Somebody's asking, would you advise your child to self-study? Jack, it's difficult. I think it depends on their motivation levels, but definitely it can be useful for many students, but sometimes you need a bit of guidance from a teacher or a tutor. Is it too late to buy the premium plan? Not at all. Majority, you still have it for the next couple of months. I just do a one-off price. It's not like you've only got it for a few more months. I just do a one-off price. It's like you buy it once, you never have to buy it again. So if you want to buy the premium plan for A-level or GCSE, then I personally think you should, but it's up to you. If you buy it and you really don't like it, just email me within a couple of days and I'll just refund you and like cancel your account. So if you buy it and go, this is crap, and it's just not what you need, I'll just refund you. Obviously, if you do that in a couple of days, I'm not going to refund you after your exams when you say, oh, I only bought it a couple of months ago. Will I go through some practical papers? I'll definitely be doing lots more kind of practical questions in the run-up to the exams, because I know that's a bit that people do find quite tricky and so on. So yeah, I'm going to be doing lots and lots of different bits and pieces. But yeah, thank you everybody for joining me in the live stream. Do I have anything similar for astrophysics? Sorry, that's another question. Not yet. I've got videos for astrophysics, for AQA, but I don't have work solutions yet. Basically, I just need to multiply myself by a factor of 10 and like train up 10 people with my own handwriting to do more stuff. But I'm getting there, but I've got lots of stuff but not everything. Right, I'll see all of you tomorrow at 8 o'clock. Have a good evening, have a good day tomorrow, and I'll see all of you then.